Isn't that just green? No. Well, yes, but it's not green. The green you'd see in real life at the top here isn't the green that your monitor displays, because it can't. And this weird blob thing has everything to do with it. This blob is named the CIE 1931 color space created by the CIE, or Commission Internationale de l'Éclairage, or International Commission on Illumination, in 1931 to standardize how we measure colors. These color spaces were a game changer. For the first time, we had a way to mathematically define colors based on human perception. The CIE 1931 XYZ color space, which gives us that iconic horseshoe diagram, was designed to encompass all colors visible to the average human eye. Now, notice the triangle inside the horseshoe. This represents the sRGB color space, the standard used by most monitors and digital devices. Any color outside this triangle simply cannot be displayed by a standard monitor. The most obvious limitations are in the greens and cyans at the top of the diagram, and some of the deep reds on the right side. Want to see more colors? Sure, you just need to get a better monitor. You might have heard of other color spaces, like Adobe RGB. Developed specifically to capture more of those cyan green hues achievable with CMYK printers, it offers a significantly larger gamut than sRGB. Look at how its triangle pushes further into the greens. That's why it's the go-to for professional photography and print work. When a nature photographer needs to capture the exact emerald tone of a rainforest canopy, they're relying on Adobe RGB's expanded green range. Then there's DCI-P3, the standard used in the digital cinema industry. It focuses on expanding the red and green range compared to sRGB, aiming for more vibrant movie experiences. Those stunning sunset scenes in blockbuster films, they're mastered in P3. Many high-end monitors, TVs, and even smartphone screens now advertise P3 coverage as a premium feature. Looking even further ahead, there's Rec 2020, the ambitious standard for ultra-high-definition television and HDR content. Its triangle dwarfs sRGB, covering a much larger portion of the visible spectrum. The difference between watching nature documentaries on a standard display versus one that supports Rec 2020 is like comparing a postcard to being there in person. The physics behind these wider gamuts involves pushing the primary colors closer to the spectral edge of the horseshoe. Engineers achieve this through advanced technologies like quantum dots, nanoscale particles that emit very specific wavelengths of light when energized. These materials can produce purer, more saturated primary colors than traditional phosphors, expanding the range of colors a display can mix. But here's the crucial point. Today's video is brought to you by Mobbin, the ultimate design inspiration platform for creators like you. Imagine having access to over 500,000 real-world app screens and 80,000 user flows from 1,200 industry-leading apps, all at your fingertips. That's Mobbin. Forget sifting through conceptual designs or manually taking screenshots for hours. Mobbin empowers you to find highly relevant design references in seconds. Whether you're benchmarking competitors, researching UI patterns, or staying up to date with the latest trends, Mobbin has you covered. With powerful features like NLP search, visual search, and text in screenshot search, you can find exactly what you need, when you need it. And with their Figma plugin, you can export screens directly into your workspace. From freelancers to enterprise teams, Mobbin offers plans to suit every need. Join over 870,000 designers worldwide who are using Mobbin to create great digital experiences faster and smarter. Check out Mobbin today and elevate your design game. Links in the description below. Even these larger triangles, Adobe RGB, DCI-P3, and even the ambitious Rec 2020, still don't cover the entire horseshoe. They capture more color, pushing the boundaries outward, but there are still colors visible to the human eye that fall outside their range. The fundamental limitations of 3 primary color mixing remain, leaving those pure spectral greens at the horseshoe's edge tantalizingly out of reach. So the fundamental question remains, why? Why can't we just build monitors that show all the colors we can see, covering that entire horseshoe shape? The answer lies in the way digital displays work. Your monitor creates colors using 3 primary colors: red, green, and blue. By varying the intensity of these 3 colors, it can simulate a wide range of hues. But it's just a simulation. To reproduce those super saturated spectral colors at the edge of the CIE diagram, a display would need to emit pure monochromatic light at specific wavelengths, and your computer can't do that. Why? Computer displays fundamentally cannot reproduce pure spectral colors due to both physical and mathematical limitations in how they generate light. The issue stems from several technical constraints in display technology. First, the RGB system creates a mathematical impossibility. To reproduce certain pure spectral colors, the transformation from CIE color space to RGB would require negative values for one or more primaries, physically impossible in actual displays. A point outside the physically realizable gamut always involves a negative value of R, G, or B. For instance, reproducing certain greens would mathematically require subtracting red light, which displays simply cannot do. Second, current LED and LCD technology cannot produce truly monochromatic light. Even high-quality displays use phosphors or quantum dots that emit a range of wavelengths rather than a single pure wavelength. Even for Adobe RGB displays, green is a particularly difficult color to produce with LEDs. It is commonly made by a phosphor that emits a broader spectrum. This spectral impurity means the primary colors themselves fall short of the theoretical ideal needed to reproduce all visible colors. While laser displays could theoretically produce pure monochromatic light, they introduce their own problems. Lasers are very directional, and you want to be able to view the monitor from different angles. So you shine the lasers through some diffusing membrane. This leads to very distracting sparkle. Even with the perfect blue LEDs, which we can create, red and green are tricky. We can't make anything cheaply and effectively that emits only those perfect red and green wavelengths. Some display technologies attempt to convert blue light to other colors using phosphors or quantum dots. But these conversions are imperfect and often require filtering unwanted wavelengths, sacrificing brightness. These fundamental limitations mean that even the most advanced displays can only approximate certain colors, never truly reproducing the full visible spectrum that the human eye can perceive. But if your monitor can't display those colors, how are you seeing them right now? Well, that's the point. You're not. What you're seeing is actually your monitor's best approximation of these colors. It's using the colors it can produce to give you an idea of what these out-of-gamut colors look like. It's not perfect, but it's the best we can do with current technology. The horseshoe shape of the CIE diagram directly illustrates why monitors struggle with color reproduction. The curved edge represents pure spectral colors, single wavelengths of light that exist in nature. Your monitor's RGB triangle falls well short of these edges, particularly in the green region around 520 nanometers, where the horseshoe extends furthest from the center. This gap isn't just theoretical, it represents real, vibrant colors your eyes can perceive in nature, but your screen physically cannot reproduce. The straight line of purples at the bottom actually works in monitors' favor, as these non-spectral colors are naturally created by mixing red and blue light, something displays can do quite effectively. This is where the biology of our vision becomes crucial. Our eyes have 3 types of cone cells, each sensitive to different wavelengths of light. Our brain interprets the signals from these cells to create our perception of color. This trichromatic nature of our vision is precisely why displays can use just 3 primary colors to simulate most colors we see, but it's also why they hit a wall when trying to reproduce pure spectral colors along the curved edge. The fundamental physical challenge remains. Reproducing these pure spectral colors would require either negative RGB values, mathematically impossible, or monochromatic light sources, technologically impractical for consumer displays. Our vision system can be fooled by clever mixtures of light for most colors, but not for those at the extremes of what our eyes can perceive. Did you know that pink doesn't exist either? Curious? Check out my other video on why pink doesn't exist.